Hey everyone, in this video, we'll be solving a really good problem from a book called University Physics by Young and Friedman. Here we are choosing today's topic to be uh, from magnetism, and here is the problem. So first read it carefully, pause the video and read it carefully. Here is the diagram and try to solve it on your own. Okay, so now let us discuss what is happening here. So let me read it first. A particle with charge 2.15 microcoulomb and mass 3.2 into 10 to the power minus 11 kilogram is initially traveling in the plus y direction with a speed v naught equal to 1.45 into 10 to the power 5 meter per second. Okay, so it's describing this particle here which has a charge 2.15 microcoulomb. Okay, it has a velocity v naught. Let's write it 1.45 into 10 to the power 5 meters per second. Okay, and its mass is also given, which is 3.2 into 10 to the power minus 11 kilogram. Okay, now it then enters a region containing a uniform magnetic field that is directed into and perpendicular to the page in this figure. Okay, so as you can see, the B vector is perpendicular to the this plane of paper, and cross means directed towards the inside of the screen or the paper. It's directing inwards. So here it is. Then the magnetic field, magnitude of the field is 0.420 Tesla. Okay, B equals 0.420 Tesla. The region extends a distance of 25 centimeters. This thing is 25 centimeters in width. Okay, along the initial direction of the travel. So it's traveling in the plus y direction, and its extension is 25 centimeter. This fielded region, and 75 centimeters from the point of entry into the okay, what then? 75 centimeters from the point of entry into the magnetic field region is a wall. This is the wall which is 75 centimeters from the initial point where the charge enters the magnetic field. So this distance remains 50 centimeter only. 50 centimeters only. It's also written. When, okay, when the charged particle enters the magnetic field, it follows a curved path. Yes, we know that we'll be talking about that in the discussion. And its radius of curvature is r, capital R. So this is denoted here as well in the diagram. It then leaves the magnetic field after a time t1. This whole journey in the curved path takes t1 seconds time, having been deflected by a distance delta x1. This small distance, small gap, is delta x1. The particle then travels in the field free region, this region, and strikes the wall after undergoing a total deflection of delta x. This amount of deflection is there total in total. So we have to determine these 1, 2, 3, and 4 things, which are the radius of curvature, the time t1, the small deflection here after leaving the magnetic field, which is delta x1, and at last we have to determine the delta x, which is the total deflection when the charged particle hits the wall. So to solve this problem, we need to know few things first. Let's study those things in a bit detail. So we know that when a charged particle having some velocity v enters a magnetic field, it is acted by some amount of force by the magnetic field, which is perpendicular to the velocity vector of that charged particle. Let's say magnetic field is in the direction such that it's directed towards the plane of paper and perpendicular to it. It's going inwards, just like this. Here's the B vector and a charged particle. Let's denote it by a new color. Here it is. A charged particle having a charge q and velocity v enters the magnetic field here. So, if there was no magnetic field in this region, it would have gone in this direction, straight line. But due to the force, which is denoted by F vector here, F vector as we know is proportional to Q times V vector cross B vector. The force is defined as this. So as the charged particle enters the magnetic field area, a force F is a force F acts on the particle, and by left hand rule we can pretty easily uh, find the force vector. Okay, so as the B vector is directed towards the screen, so the force vector would be upward, and as the velocity is also towards the plus x direction. Here let me give you a perspective here. Here it is x, y and z. So the force would be acting in the plus y direction. Here B vector is in the minus z direction. Velocity v is in the plus x direction. So the F would be in the direction positive y. So as the force is acting perpendicular to the velocity, it would not be changing the velocity's magnitude, but it would be changing the direction of the it would be changing the direction of the velocity. Okay, and it would be always acting perpendicular to the velocity. So it would mean that this particle will do a circular motion in this magnetic field. So first thing is here, if as F vector is perpendicular to velocity vector, the velocity's magnitude would be constant, but the direction changes. As there is a force acting perpendicular to the velocity, so we can say that due to this force, it would be doing a circular motion having some radius r. Let's draw this diagram again carefully. Here is the circle, charged particle here having velocity v. Let's take the magnitudes first. Here by the cross we denote the b vector, and the vector will be towards the center of the circle O. Let's assume that this circle has a radius of r. So F vector is q times v cross b. So if we take the magnitude of f vector, we can say that q times v vector's magnitude into b vector's magnitude into sine of angle between v vector and b vector, which is here pi by 2. We have assumed that angle between v vector and b vector is pi by 2. So so the particle enters the magnetic field region perpendicularly. Okay, so here it would be equal to 1, and this angle is pi by 2. So we can safely terminate this term. So force vector is simply qvb. We can write it like this, qvb. And as it is doing a circular motion with radius r, it would be having a centripetal acceleration. It is having a centripetal acceleration ac. So F is equal to mass of the charged particle m into ac, which is m into v square upon r. So by these two equations, we can conclude that q v b equal to m v square upon r. One v cancels out. So here we get that r, which is the radius of the curvature, is equal to mv by qb, which is equal to the magnitude of the momentum of the particle. Let's write it as p by qb, sorry. So we have to calculate this r in the question A. So here I have written all the data from the question: the charge, the magnetic field, velocity, and mass of the charged particle. So from the earlier discussion, we have concluded that the radius of curvature r is equal to the momentum of the particle, magnitude of momentum, by the charge into magnetic field. So mv by qb. Here m is 3.2 into 10 to the power minus 11 kilograms. Velocity is 1.45 into 10 to the power 5 meters per second. Q is 2.15 microcoulomb, and magnetic field is 0.420 Tesla. So we will calculate this. Let's use a calculator. I'm using Desmos here. 3.2 into 10 raised to minus 11 multiplied by the velocity 1.45 into 10 raised to 5 by the charge 2.15 microcoulomb and 0.420 Tesla, which is approximately 5.138 meters. 138 meters. So here is the radius of curvature of the curved path. Option A. In the second question, we have to determine T1 the time the particle spends in the magnetic field region. So let's solve this. Let's go to the diagram. So here is the charged particle which is projected along the y-axis with a velocity v0 as discussed earlier. The total width of this magnetic field region is 25 centimeters as given in this figure. And here is the deflection delta x1. Let this angle be phi. So R is the radiature of, sorry, it's my spelling mistake. Radius of curvature. So we can draw a perpendicular line along parallel to this, let's say A B, and this is C D. So R sine phi can be written as 25 into 10 to the power minus 2 meters, as R is in meters. So from here we can calculate it easily. So as we have seen, R is R into sine phi is 2.5 into 10 to the power minus 2 meters. So sine phi is 2.5 into 10 to the power minus 2 upon 5.138. So phi is sine inverse 2.5 into 10 to the power minus 2 upon 5.138. If we calculate this, sine inverse 2.5 into, okay, sorry, it's 25, not 2.5, 2.25 centimeters. 25 into 10 to the power minus 2 into 10 raised to minus 2 upon 5.138. In radians, it is 0.0486762 radians. Okay, so phi is this. The charged particle has a velocity 1.45 into 10 raised to 5 meters per second. So its radius of curvature of circular motion is 5.138 meters. We know that for circular motion, angular velocity is v upon r. So we can calculate its time period of circular motion, 2 pi by omega. So to rotate 2 pi, it takes t seconds. To rotate 5 radians, how much it would take? T up into 5 upon 2 pi, which is equal to T1. T1 equal to T into pi upon 2 pi. Okay, so which is capital T? 2 pi by omega. 2 pi. And what is omega? V upon R. 2 pi R upon V into 5. What is pi? 0.0488662 upon 2 pi. 2 pi gets cancelled. So 5.138 into 0.0486762 upon 1.45 into 10 raised to 5 meters per second, which will give us the time t1. Let's calculate it. 5.138 into 0.048672 by 1.45 into 10 raised to 5, which is approximately 1.72 into 10 raised to power minus 6 seconds. So here is the second answer of the question. So we can also say that 1.72 microsecond. Third question we have to tackle is determine delta x1, the horizontal deflection at point of exit from the field. So here delta x1 is this tiny portion of space by which the charge will be deflected when it exits the magnetic field. So this is R. Wait a second. This is R and this is phi. This angle is phi. So we can say that this up to D is R cos phi. So delta, we can say that in the C part, delta x1 can be written as R, the total radius, minus R cos phi. R, let's take it common, 1 minus cos phi. R is 5.138, 1 minus cos phi is 0.04866762, which is 1 minus cos 0.04866762 into 5.138, which is approximately 0.0060857 meter. This is the delta x1, which is equal to 0.60857 centimeters. In the fourth problem, and it is the last problem here, determine delta x, the total horizontal deflection. If we see the diagram, then we can see that this delta x1 includes this delta x here includes this small deflection delta x1 as well. Let's assume that this part is del. So we can say that delta x equal to del plus delta x1. Okay, so here this angle is phi, this is pi by 2. So this is pi by 2 minus phi. This is also pi by 2. So this should be again angle phi. Okay, this is 50 centimeters. As you can see, this is 25 centimeters and total distance capital D is 75 centimeters. So this remains 50 centimeters. And this is del. So we can say that in D part, tan phi equals del upon 50 into 10 raised to power minus 2. So del is equal to, okay, let's take the del as in centimeters. So the calculation would be a bit easy. Although we are using calculator, my bad. 50 into tan phi. Here phi is equal to 0.048 672 radian. So del is equal to 50. It's in centimeters. 50 into 10, 0.048676762, right? 6762. Okay, a bit out of, we are having a shortage of space. So let me shrink it a bit. This is the power of having a pen tablet. So del can be written as, please ignore the background noise, 50 into tan 0.0486762, which is approximately 2.4357 centimeters. So delta x would be del plus delta x1. Here del is 2.4357 and delta x1 is 0.60857, which would be, let's use it for the last time, 2.4357 plus 0. Actually, it is a bit messy here. 0.60857, which is 3.0447 centimeters. So this is the answer to our final question. So this is all done. So if you have find this video a bit useful for yourself, then please like, share, and comment what kind of problem should I try next in this channel. And don't forget to subscribe Decoding Physics and share it to your friends and families. And best wishes to all of you.